Hello, thanks for watching my talk. This is work that I did as part of my dissertation at the University of Colorado, where I was working with Dave Brain. And though this is a session dedicated to understanding global magnetic fields, my work has focused on magnetic fields on a slightly smaller scale. Specifically, I've been studying the magnetic environment of Mars, analyzing how magnetic fields locked into the planet's crust might act as a microcosm through which we could gain an understanding of the effects of global magnetic fields. If you're unfamiliar with Mars's crustal magnetic fields, here I'm showing a map of where they are found across the planet's surface. Red means the magnetic field is coming out of the surface, and blue means it's going back down into the surface. And the resulting structures are these loops of magnetic field that act like miniature magnetospheres. In a simplified sense, the structures look something like this. We have these loops of closed field that divert and deflect incoming particles, potentially shielding the atmosphere. And then we have these cusps of vertically oriented open fields that link up with the solar wind, channeling energy input into the atmosphere and potentially driving enhanced particle escape. This setup is reminiscent of what we often discuss with regards to global magnetic fields. Magnetospheres do shield a planetary atmosphere in some ways, but they also provide a large target to capture energy that might then be channeled down into polar cusp regions. So, we have some regions that likely decrease atmospheric escape and some regions that likely enhance escape. A natural question is, what is the net effect of having these fields there at all, as opposed to a planet that just didn't have crustal fields? We're interested in this both for understanding the history and evolution of Mars and how it relates to Martian habitability, as well as for understanding those broader questions of planetary magnetic field effects in general. In order to study this, I'm going to be using the MAVEN spacecraft, which is flying through these crustal magnetic fields and making direct measurements of escaping particles as well as the magnetic fields themselves. In studying ion escape, there are three main factors that we need to consider. These are the supply, energization, and transport of ions. First up is the supply, which is just asking where are ions created. If we don't have ions, then we won't have ion escape, a pretty simple idea. And measurements we can make to inform us of this would be something like ion densities. Next up, we need to understand where are those ions gaining enough energy to actually escape the planet. Measurements that can help us figure this out would be something like ion velocities or ion temperatures, or in our case, we're going to be using ion fluxes. Finally, once we know that there are ions there with escape energy, we need to ask where are the ions actually able to convert that escape energy into escaping from the planet. If you're an ion that's low down in the ionosphere, you might be colliding with other particles and not able to leave the planet. Or even if you make it up past the exobase, magnetic fields might prevent you from leaving due to their magnetic topology. So to study this, we're going to be looking at magnetic topology as well as particle magnetization. Each of these steps could represent a bottleneck for escape under certain conditions. If the supply of ions is low, then escape rates are going to be low regardless of how much energy is delivered to the system. If many ions are created but energy input is low, then not many ions will reach the velocities they need to escape Mars. And even if many ions are brought to escape energy, they still might fail to be transported out of the system due to the factors we just discussed. Okay, so let's dive in. Here I'm showing geographic maps of ion density across a range of different altitudes at Mars as measured by MAVEN's static instrument. This is ranging from 200 kilometers altitude in the upper left to 1,000 kilometers in the lower right. And in this talk, I'm going to be focusing on O2 plus and O plus ions, since these are the dominant species at these altitudes. At lower altitudes, we can see that there's uniformly high densities across the whole planet. But as we move up to higher altitudes, we can see this region of higher densities found in the southern hemisphere, right where the strongest crustal fields are located, if you'll remember the map that I showed at the start. This is telling us that the crustal fields might be holding an enhanced supply of ions. Unfortunately, there's a decent amount of statistical noise on these maps. Some of the bins only have 5 to 10 points in them, so it's helpful for us to plot this on a different set of axes, which is shown here. So here I'm once again plotting ion density, but now the x-axis is crustal field strength below the spacecraft, as inferred from a model. So on the right side of each plot are regions with strong crustal fields, and on the left side of each plot would be regions without crustal fields. And the y-axis is altitude above the planet's surface, and I have one plot for O2+, and one plot for O+. Once again, we can see that at the lowest altitudes, we have high densities basically everywhere, but as we move up in altitudes, we find higher densities in crustal field regions. The interpretation here is that the vertical fields we find in crustal field structures are more able to transport plasma up to high altitudes, and that the strong crustal fields can trap this plasma more effectively. In comparing O2+ and O+, we can see that O+ densities are lower, especially at low altitudes, but that the trends shown are generally the same. One final thing to note here is that in these plots we can see a steep drop-off in density found at higher altitudes, particularly in non-crustal field regions. This is representing the boundary into shocked solar wind plasma, and we can see here how the presence of crustal fields affects that boundary, pushing it up to higher altitudes. Okay, that was the supply. Now let's look at the energization. I'm showing things on the same sets of x and y axes, but now the color is showing us the flux of ions moving upwards with energy greater than escape energy on the day side of Mars, basically flux of escaping ions. We can still see in the upper left-hand part of these plots the boundary into the solar wind plasma, and we can also see that just below this boundary we see pretty high escape fluxes. As you move down to lower altitudes, though, we see some differences between O2+ and O+. Specifically, O2+ doesn't seem to reach escape energy at these low altitudes, whereas O+ does. The reason for this is likely that O2+ requires higher escape energies to leave Mars, just because it's a heavier ion. And so, while O+ might be energized by ambipolar potentials, which have been reported around Mars to be about 1 to 2 volts basically everywhere, this would bring O+ up to escape energy, but would not bring O2+ up to escape energy. Rather, O2+ would just get lofted up to higher altitudes, and only upon reaching those higher altitudes might it interact with some other energization mechanism, heating of some sort. And then at those higher altitudes, O2+ can then reach escape energy. We can also see that across magnetic field strength, there is a variation in where this energization is occurring. Notably, in this O2+ panel, we can see that as you move to the highest crustal field strengths, the altitude at which these particles are being energized seems to get higher and higher. Our interpretation here would be that these particles are getting energized at the tops of crustal field structures through some form of interaction with the solar wind. This might be some kind of wave heating or magnetic pumping, but I don't dive into the specifics of the mechanism here. Okay. So that was a lot, but we still have one last piece in the puzzle, and that's the transport of ions. Are these ions actually escaping? Well, part of understanding this is looking at magnetic topology, and we can look on this same set of axes where we find open or closed magnetic fields. To determine magnetic topology here, I'm using a method that I developed with Xiaosui Zhu at Berkeley, where we take in information from electron energy spectra and electron pitch angle distributions to figure out the end connections of magnetic field lines. In the left plot, I'm showing the frequency of observing a closed magnetic field line in that part of parameter space. 1 means that we see closed fields 100% of the time, and 0 means we see them 0% of the time. In the right plot, I'm showing where we see frequency of open field lines, and we can see that open field lines are found more commonly at high altitudes and in weaker crustal field regions, whereas closed field lines are found more often at low altitudes and in strong crustal field regions, as we would expect. By combining this information on these plots with the information of our flux measurements, we can start to get an idea of true escape numbers, but to make things more complicated here, we need to think about how topology only matters if particles are really bound tightly to the magnetic field. Though we often think of particles as neatly orbiting around magnetic field lines, real magnetic fields aren't nice like this. They twist and turn and have small-scale variations, and if a particle's gyro radius is large in comparison to the changes in magnetic field, then the particle won't stay trapped on a single field line. So we analyzed how magnetized ions are. To calculate this, we use magnetic field data measured by MAVEN, and we calculate first the gyro radius of an ion at the energies we're measuring, and second the characteristic length scale of the local magnetic field. To get that length scale, I'm taking the magnitude of the magnetic field and dividing it by the magnitude of the gradient of the magnetic field. This length scale L then basically represents how far one would have to travel for the magnetic field to change by 100%, given its current rate of change. Then we can make these maps of gyroradius divided by L, where a high value means that the gyroradius is comparatively large, so the particles are unmagnetized, and a low value means the gyroradius is comparatively small, so the particles are magnetized. We can see that particles are most magnetized at low altitudes and in the crustal field regions, and if I plot this on the same set of axes as before, we can see the same trend, where ions are only magnetized at low altitudes and in strong crustal field regions. There's a transition region on this plot where the color is switching from red to blue at a value of 1, and this is telling us where particle gyroradii are just reaching the same size as magnetic field length scales. This transition appears to be happening at roughly the same altitude band as where ions were reaching escape energy, as was shown on our flux plots. And that's shown here. So, with the knowledge that our ions are only partially magnetized, I'm now going to combine all this information to make some estimates of crustal field influence on ion escape. I'm going to make two estimates, one of which is the influence on global ion escape, and one of which is crustal field influence on local ion escape. In doing so, I'll be dividing the data into three groupings of magnetic field strength, shown here, and I'll also be restricting our focus to the altitudes where the escape is likely happening rather than using the whole altitude range so that we don't double count particles. In the weak field regions, all of the ions are unmagnetized, so we're going to take all of the escape energy flux we measure here as leaving the planet, regardless of whether or not it's found on an open or a closed magnetic field line. In the medium strength crustal field regions, ions are partially magnetized, so here we're going to introduce a free parameter alpha. We say that all escape flux measured on open field lines in this region will escape, but that on closed field lines only some fraction alpha of it does. And in the strong crustal field regions, particles are once again partially magnetized, so we introduce a separate free parameter beta, and once again say that all escape flux on open field lines escapes, but that on closed field lines only some fraction beta does. Then we take all these fluxes, multiply them by the area covered by magnetic fields at these strengths to get outflow rates, and we arrive at this plot here. And this is showing O2 plus total global escape rate as a function of alpha and beta. As a reminder, this came out of this formula here. So, where alpha is 0 and beta is 0, this would mean that in medium and strong crustal field regions, no particles found on closed field lines are able to escape. Where alpha is 1 and beta is 1, on the other hand, represents particles being so unmagnetized that any particles moving upward with escape energy leave the planet, regardless of if they're on a closed or open field line. And the dotted line on this plot is a calculation of the escape rate that we would have if there were no crustal field structures on Mars. This was estimated by taking the escape rate that we have in the non-crustal field regions, in green, and multiplying it by the full area of Mars. So, one main thing we notice here is that the entire range of values that we calculate doesn't stray too far from this dotted line. At most, crustal fields are affecting global ion escape by 40% or so, and for most of the values represented here, they seem to be decreasing escape by about 20%, which is a number that's in line with previous modeling studies. Just as a note, I made the same calculation for O+, and though the escape rates are slightly different, the trend shown is the same as the one here. My final estimate here is of the influence that crustal fields have on local ion escape, not caring about the global distribution of those fields. This might have some more direct implications towards the question of whether planetary magnetic fields matter, and it involves just a more direct comparison between the escape fluxes in crustal field regions and non-crustal field regions. The range of values that result from alpha and beta going from 0 to 1 are shown here, and we can see that in order for crustal field regions to have escape fluxes equal to those in non-crustal field regions, they need to have an alpha and beta value of 0.6 and 0.65 respectively. Or in other words, in order for a region with crustal fields to have the same escape rate as a non-crustal field region, 60% of the particles found on closed field lines with escape energy do need to escape from the planet. So, wrapping up, our main takeaways here are that crustal fields affect global ion escape by at most 40% and local ion escape by at most 80%. And finally, that only with significantly unmagnetized ions could crustal fields increase local ion escape. These last 2 points might have some direct applicability towards the question of planetary magnetic fields in general, but how well we can apply them remains to be seen. Thanks, and I look forward to talking to you during the session.